Okay, so now we're going to focus in on actual cues, not just like an idealized system like our two-level system, where we only have like two actual energies we can visit. We're going to look at cues for ideal gases, and then we're going to actually use them to calculate observables. The thing about Q is you'll see it referred to as the StatMet wave function. Okay, I don't want you to get confused with that where you kind of treat it like a wave function. That's not why we call it that. The reason that it's referred to as a StatMet wave function is because just like a wave function in quantum mechanics, when you know it, you know how to calculate all your other observables. Okay, so without showing you the derivations, there's a series of calculations that you can do where all you really need to know is Q, all right? And instead of having to do the sums that we reference, where you have like a probability times what you're trying to observe, okay? You can manipulate those sums into these expressions. So for example, internal energy, which is the average energy, is KT squared, partial the natural log of Q, partial T at a constant N in V, okay? So this is a thing where if I can figure out what Q is for a system, okay, I can just plug it in here and then I got my U directly. So a lot of StatMech is what can we do to make a functional form of Q. Same thing for average pressure. Notice it's not a small p, it's a big P. Average pressure would be like the pressure we measure for a system. Just like average energy is the internal energy that we measure for a system. And this is KT, partial natural log of Q, partial V, at a constant N and T. Okay. Entropy S is KT d natural log of Q dt N V, all right, plus K natural log of Q, all right. And if you look at U and you look at this first term here, these two are the same except U has an extra T. So sometimes for S, definitely know this form, but sometimes for S we write this, right, as U over T. Because mathematically, it's the same as that expression that was there. It looked exactly like this, but with a T taken away. So with this, and then realizing that in the canonical ensemble, we always specify N, V, and T. We have all the important thermodynamic variables that we've ever talked about all semester. We have a U, we have a P, we have an S, and then we know we're setting up our system with a T and a V that's known. We have everything that we need now to build any other thermodynamic quantity. And again, what's the only unknown in this? The only unknown is Q, okay? K is known, T is specified, okay? All we need is Q, and then we can bring StatMech to all of these observables that we've looked at throughout the whole entire year, okay? So a quick little example on that. We know that H is defined as U plus PV. So what we can do if we wanted a StatMech description of H, okay, is we could use our definition of U, which was K T squared partial natural log of Q partial T at a constant NV. We could use our definition of P, all right? And then whatever our definition of P is, all we have to do is multiply it by V. So this looks like KTV, because remember, that's specified by our canonical ensemble. It's one of the variables that we make sure we hold constant, N, V, and T, when we actually make our ensemble. So this is KTV, all right? D, the natural log of Q, dV. These are partials, even though I'm saying D, just like always, at a constant N and T. So now I have what H is, and again, if you look at H, T is specified, V is specified. Really the only thing that I don't know is Q, and that would be the thing that I would have to analyze. So how do we come up with Qs? For systems unlike, all right, the two-level system, so beyond like just model systems, how do we determine Q? All right, well, Q is determined by looking at individual Qs, okay? So I'm going to write down this expression and I'm going to tell you where it comes from. And what I mean by individual Qs is every motion has its own small q. Every motion has its own little energy level diagram. You put all the motions together for a molecule or a particle, and then that gives you your overall q. Okay. So what our big Q expression looks like, and again, we're going to make some statements without derivation, is it looks like a product of individual Q's. And these individual Q's we reference as small Q's, and there's going to be one for each motion, right? You take your product and you raise it to the n, and you divide by n factorial. And we're just going to take this as a definition for now, right? And for the semester in our abbreviated way, okay? And then we're just going to have to know how to use it. So what we do then is we use this definition. We say, okay, well, what motions are there? So for the thing that we're trying to analyze, what motions are there? Is there a bond? So there are vibrations, right? And if there's a bond, there's rotations. All things move, so we know there's translations. But we also know there's things like monatomic ideal gases that don't have bonds, so there won't be any vibrations and rotations. Do things have electrons? Because if they do, then we know that there are electronic energies that we would have to calculate. Every motion that you can describe, any motion that you can identify for a particle, that's something that you translate into a small q, right? A small q. So for example, the most complicated example we can think of right now, right, at our level of understanding is, right, a polyatomic molecule. Think of something like H2O. All right. Can H2O translate in space? Yep, it can move around in 3 dimensions. So it has a small q trans. And then I could analyze the energy levels for translational motion using like a particle in the box, and I could build this, right? Can this guy rotate? Sure. So then it has a small q rotation based on the idea that this guy can move around over 3 different directions. It can rotate. There's 3 different moments of inertia. Are there vibrations here? Yep, there are vibrations there. So if I look at the rotational energy levels, I can get a q rot. If I look at the vibrational energy levels, say using a harmonic oscillator approximation, I can get q vibe. Okay. Are there electrons here? Sure. So then I could look at those energy levels and get a q elec. So hopefully that's making sense. What I would get for big Q for this situation using this formula is it looks like, I take all my individual Q's, and remember this notation here. Whenever you see capital pi, it's like a sum except it's saying, hey, multiply everything. Don't add it together. So big Q is going to be equal to Q trans times Q rot times Q vibe times Q elec. Now, to be honest with you, there's also nuclei there that have energy levels. All right, they end up not really affecting things that much, but any energy you can think of, and we'll just focus on these main ones, the ones that we studied last semester. There is a small individual partition function that combines to give the big partition function. Now, this isn't quite this up here. We don't only multiply these together. What else do we do? We take them and we raise them to the n, right? So we use the number of particles as an exponent, and then we divide our whole entire expression by n factorial. Okay. So hopefully you can see with this example, you say, okay, well, what kind of motions are there? You can build a big Q from there, and then big Q is what goes into our expression for energy and entropy and pressure, and we build everything from knowing big Q. Okay. I will point out one other thing. Because Q is a multiplication, right? What you'll see is when you look at that energy expression, is inside that energy expression, I'm just going to do this real quickly. It's like kind of proportional to, there's a natural log of Q term in there. And whenever we have a natural log of Q, kind of think about this. This is going to break into a natural log of the small Q's plus the natural log of another small Q. Like say Q1 is Q trans and Q2 is Q vibe. They break into a sum, And that's important to know because if I'm looking at energy, my energy looks like a sum of all the individual contributions. So, for example, what this ends up meaning is I could look at average total energy, which involves total Q, or I could look at actual energy of vibrations or average energy of vibrations. And for these, it looks like the exact same formula, kT squared. But if I'm just looking at the vibrational component of energy, unsurprisingly, instead of having a big Q here, I'm just going to use the Q for the vibrational motion. Every motion has its own every motion has its own energy level diagram. So every motion has its own small q. The small q's combine to give you a big Q, all right? A big Q, okay? But every individual like sort of motion contributes to the total energy, right? I could write an E rot that has Q rot here, an E trans that has E trans here. And then if I wanted the total energy, I could add them all together. And that comes intrinsically from our definition of big Q. Okay. So again, they're just definitions that we have to know without actually justifying them from a derivation standpoint. So here's how it's going to work for me, all right? I'm going to throw small Q's at you, or I'll throw throw the small Q's at you or big Q's. I won't have you drive them. You don't need to know where they come from. But if I give you one, you need to know how to plug it in the correct spot, all right? And then analyze the results from there, okay? To drive this point home, we're going to show you some magical stuff today. And what we're going to look at is a monatomic ideal gas. Let's say we wanted to approach this from a statistical mechanics standpoint. We have to think about the types of motions that it has. So think about like argon or something like that. And it's an ideal gas, so there are no interactions. So really, there are just motions there. So what can argon do? Can it vibrate? Well, no, it doesn't have a bond. It doesn't have a bond, so it can't rotate either. It has electrons, all right, and it definitely can translate. So big Q in this instance looks like Q trans times Q elec to the n over n factorial. Now we mentioned it earlier, so we're going to do a simplification here. Remember what Q elec would be? We're going to monitor this near room temperature for this example, okay? Q elec I'm going to set to 1. Now, why does that make sense? Remember, the energy gaps for electronic transitions are big. They're UV, right? A few of them are Viz, but they're UV. They're big gaps relative to the other gaps that we're talking about. Essentially, most things are in their electric ground state. So what does Q elec measure? The number of thermally available states. So to a good approximation, we're going to say, yeah, there are electrons there, but only one electronic state is thermally available. So I'm going to set Q elec to 1. So a real good big Q then is Q trans over n factorial and raise that Q trans to the n power. Okay? So now here's where I would come in and I would say, okay, well, having analyzed this in this fashion, I'll tell you that Q trans is equal to this value, okay? It's equal to 2 pi m kt over h bar squared to the 3 halves, right, v. Now, it's kind of an interesting derivation. You'll probably read it, but it's not something I'm going to ask you to reproduce. But Q trans looks like this. So now this is all I need to get big Q. Because what does big Q say? Well, big Q says take this Q trans, raise it to the n power, and divide by n factorial. So big Q for this monatomic ideal gas, which only has translational motion, looks like 2 pi mkt over h bar squared raised to the 3n over 2 v to the n divided by n factorial. So all I did was take this, which I would give you, and I gave you for this example, and throw it into our definition of big Q. Okay. Now, this is all we need to start to analyze information about monatomic ideal gases. For example, what's the internal energy for monatomic ideal gases? Well, that looks like K T squared partial natural log of Q partial T at a constant V and N. All right. Well, I know that Q depends on T, so I'm going to start to analyze this. KT squared, and I'm going to drop these constants. We're going to realize they're a constant, but I'm going to kind of get lazy about it. I'm going to write this as partial natural log of Q, partial Q, partial Q, partial T. Okay. Now this is the way I like to approach it. Your book approaches it a slightly different way. Whatever makes sense mathematically for you, you enact. So I like to use the chain rule here because I know Q is a function of T and I have a natural log there. And then this is a real easy derivative to analyze because I get 1 over Q here. So this looks like KT squared, right? 1 over Q, and then we have partial Q, partial T that we still have to analyze. So where's T inside here, right? T shows up here. Everything else inside Q, remember this is a partial derivative, is constant. So everything else gets brought out front, and T is the only thing that you take the derivative of, okay? So if we do that derivative, we got KT squared over Q on the outside, right? Let's pull out all our constants. 2 pi m k over h bar squared, right? Raised to the 3n over 2. V to the n over n factorial, also pulled out as a constant. Do this temperature derivative. You're going to get 3n over 2, okay? Then you're going to get T to the 3n over 2 minus 1. So the T is raised to the 3n over 2 power. So you bring it down and you subtract 1 from the exponent. And that's what you're left with for the expression that we're now analyzing. Okay. Well, hold on a second. If I go back and I look at my Q, right? Q is mostly there. And in fact, if you look at this T, this part, right, is Q, except the T stuff is missing. But if I look here, right, we do have a T to the 3 halves n, right, or a T to the 3n over 2 that we could kind of bring back inside this fraction if we wanted to. So what I'm going to do is I'm going to write this in a way where I can see what actually happens to reproduce Q. Okay? So let's do some rearranging and see what I'm talking about here. And I'm going to keep Q up here just so you kind of see what's happening. I'm going to rewrite T to the 3n over 2 minus 1. I'm going to rewrite this as T to the 3n over 2 over T. I'm just going to use the property of exponents there. Remember, subtracting an exponent is like you divided by that same thing and it was in the denominator, right? Just use some exponent algebra. I have a T squared here, and now I have a T in the denominator over here. So one of these cancels, and then look what I have. T to the 3n over 2, which can get brought back inside this right here to regenerate my Q. Now I'm doing a lot of this verbally, but make sure you can write down the intermediate steps and understand what's happening here. So if I look at organization here, my internal energy is a KT over Q out front, right? I'm going to bring that part of T back inside here to regenerate Q, right? What I'm left with here is 3n over 2 that came from my derivative, all right? My Q cancels my Q. And so we get this important result that we actually got in a different way last semester. Okay. We get that U is 3/2 NKT, right? For a monatomic ideal gas with 3 bits of translational motion, with 3 different degrees of freedom for translation, you get that U is 3/2 big NKT. Remember, we can make this a molar quantity by dividing by small n, the number of moles. And then also remember that big N over small n, particles per mole, that looks like Avogadro's number. And then just like last semester, N sub A times K is equal to R. So there's a couple different things that all mean the same thing here. Just going to go over them one more time. For a monatomic ideal gas, knowing this, and it was the only thing I needed to know, led me to mathematics that told me that the internal energy was 3/2 NKT. The molar internal energy, right? The molar internal energy is 3/2 N over N. It's 3/2 RT. It's 3/2 RT. Okay, that's the molar value. Okay, really important results. Because what we can do with this then is we can go and we can ask ourselves, okay, well, anytime I saw any thermodynamic quantity that involved U or molar U, I know what that is now. I know what it is for a monatomic ideal gas, so now I have an expression that I can analyze in that way. For instance, for a monatomic ideal gas, molar CV, we know from earlier in the semester, is partial U, partial T at a constant V. Guess what you can do? You can take this molar U that we have right here, 3/2 RT, and you can throw it in there. And from a stat mech standpoint, what do we get? We get the exact same result we've been getting all semester for CV for a monatomic ideal gas. When I take the temperature derivative here, what happens? The T goes away. So you get that molar CV is 3/2 R. Incredible. It came from this. It came from a completely different thought process. It came from a completely different analysis, looking at the translational motion of available states for a given temperature, looking at the partition function. And what do we get? Something that we've been using all semester that we just kind of stated as fact. And this is where it's really coming from. Okay. What about a delta U for a monatomic ideal gas? Okay. Remember, molar U is down here. What if I wanted a delta U? Well, I'm going to do U2 minus U1, right? U only depends on temperature. Again, something we've been saying throughout the whole entire year for monatomic ideal gases. So this U2 minus U1 is really 3/2, right, RT2 minus 3/2 RT1. Okay? So delta U is really 3/2 R T2 minus T1, which is really 3/2 R delta T, which is really CV delta T. And what did we say at the beginning of the semester about how you calculate delta U no matter what for an ideal gas? It's always CV delta T. And where did this come from? Again, stuff we've been using all semester came from, and I know we couldn't do the derivation, but this thing right here, this ultra important thing, right, that we were able to infer by looking at the small q and the types of motions that we had, lead us to a CV that we recognize and an expression for delta U that we also recognize. Okay? You can do the same thing for pressure, right? Same thing for pressure. And I want you to try this on your own. So I want you to use this big Q, right, that we have when we wrote down in the previous example. And we know that pressure from a stat mech standpoint looks like KT partial natural log of Q partial V done at a constant N and constant T, right? What you should be able to show is pressure looks like NKT over V, right? Fill in the mathematical steps using the Q that I give you, because that's how problems are going to work, right? P looks like NKT over V, right? We can go ahead and take this and multiply by small n over n, right? And then we see we have an n over n, which is n sub a, right? And then we have an n sub a times k, which is an r. We get that P looks like nRT over V. You get this from StatMech. Now fill in the gaps here, but we recover the ideal gas law just by looking at things from a thermodynamic standpoint. Remember, I started this video with a definition of H, not the very beginning, but we looked at a definition of H earlier. Guess what you should be able to show with your definition of H? You should be able to show that H is 5/2 RT. You should be able to show that CP is 5/2 R for a monatomic ideal gas. And you should be able to show that delta H is CP delta T for a monatomic ideal gas. Okay. Everything that we ever got in thermodynamics, you can make a pathway from a Q, from a knowing of available energy states, from looking at a ladder and figuring out what that energy level distribution looks like. You can develop everything that we've ever developed in thermodynamics from there. Okay. So this is how problems are going to work, and I'm going to spell it out one more time. I'm going to give you a small q or a big Q, and you have to use these mathematical objects. You have to use these statistical mechanical calculations. You have to use these equations and come up with things like H and A and G and anything that we ever talked about, and be able to do the math depending on what the Q looks like. All right. Now, if I go to a diatomic ideal gas, all this changes. And we kind of know that from earlier in the semester, okay? So we learned some of these for monatomic ideal gases because they're just the simplest system to work with. But if I go to a diatomic ideal gas, does Q change? Well, sure. Because if I go to a diatomic ideal gas, right, what do we have? We have rotations that we have to worry about, vibrations that we have to worry about. We have a different Q. And if you have a different Q, you have a different analysis that's enacted, the mathematics look different, and you get different values here, right? So you're going to explore some of that, but just kind of see the big picture here and what's done, right? Now we are going to do some more examples with vibrations, right? And you're in our next video, because we kind of been referencing them over the whole entire year. So if this still seems a little bit daunting, the next video will help some more. But think about this thought process, right? If we're smart enough to get Q, all we have to do is feed it into those equations, and we know everything we ever need to know about thermodynamics, right? And that's the beauty of StatMech.